This is a very cartoonish schematic of a uranium atom. The radon that we're going to be talking about comes from one and only one place, and that's the radioactive decay of radium. Radium comes from the radioactive decay of uranium. Now, one of the things you need to keep in mind here is how many of these things are reactive and in what ways, and how are they going to exist in the environment. Uranium, you see in the outer ring of electrons here, has only 2 electrons. There should be, to be a complete ring and therefore non-reactive, there would be 8 electrons at that energy stage. So with only 2, there are lots of sites for other things to chemically bind to uranium, and that's why it's in the shale, because it leaches out of the mountains and is washed down the river along with the other sediments and forms the shale when it finds a low spot. That's why most of the shale resources in this country, shale gas resources, are in the plains states, in the Midwest. Now, the oldest mountains in the world are the mountains around here, the Allegheny Mountains, the Appalachian Mountains. They have the shale from way, way back, 400 million years ago, called the Marcellus Shale. This, by the way, is what you rarely will ever see. That's pitchblende, which is pretty much pure uranium ore, these little nodule type things. Generally, the uranium that you're going to be finding in fuel cycle or in any other use of uranium is going to come from a sandstone kind of deposit, or a shale type deposit that you pick up and you crush. And the uranium content is probably 1 to 2% maximum of the matrix that you're dealing with. This is radium. This is even more reactive than uranium. Again, we only have 2 electrons in the outer band. This is one of the most reactive of the elements in the nuclear cycle. Here's our friend radon. Notice something completely different here. This outer circle is full. There are 8 electrons at that energy level in the atom. That means it's not reactive, and that's key here. Radon doesn't react with anything else. The only way to create it is for radium to decay. The only way to get rid of it is for radon to decay, right? Radioactive emission. This is the cycle. This is the decision tree, decay series. You start up here with uranium-238. There are 2 naturally occurring isotopes of uranium-238 and 235. The 235 is much less of the much smaller percentage of the uranium than the 238. And that the 235 is the form you need for nuclear power plant. So the uranium decays to thorium, it decays to palladium to uranium-234, and then you come down here, and here's where it starts to get interesting for us. Underneath here, you'll see the half-life, 4.5 million years, thorium 75,000 years, radium of 1,600 years, radon 3.8 days. What happened? Well, radon has a much faster decay chain than its other predecessors. But then it gets really exciting. Now we get to what we call in the industry the radon daughters. All my mining friends from the yellow cake industry were very interested in exposing themselves to radon daughters. They are polonium-218, lead, bismuth, and this is the chain you want to follow, is this one here. Eventually, when you get to lead-206, which is a stable isotope, the radioactive decay stops. But here's where your problems are. The polonium-210 is there, and the lead-210. Notice lead-210 has a 22-year half-life. Most everything else here is in the order of minutes or seconds, except polonium-210, 138 days, and lead-210, 22 years. So when the radon decays and gets to lead-210, it's going to be around a fairly long time. And when it decays, it's going to decay by beta decay until you get to polonium. This is the culprit that causes the lung cancer, according to the National Academy of Sciences, biological effects of ionizing radiation studies. This is a solid when it's at normal temperatures and pressures. And if that happens to be inside your lungs when it decays, by alpha decay, this one right here, that is going to damage the lining of your lungs and eventually cause lung cancer. The lead is also a solid at normal temperatures and pressures. So these are the two things you're worried about most, are polonium and the lead. If they're in your lungs when they decay, you're going to get lung cancer eventually. Let's shift to the shale. Remember I said most of the shale's in the Midwest and the Great Plains. There it is. Here we are in the Marcellus Basin. There's underneath that, there's a little bit deeper down, there's the, what's the one that started at the beginning? Utica. The Utica shale. By the way, those of us in New England have, and you'll see we're in New Jersey, we don't have a shale here. Sorry folks, there's a new one. I don't even have it on the map. It's called the Newark Shale, and I know very little about it, can't find very much about it, except it extends up into New England. It starts in eastern Pennsylvania. It's interesting, it starts in Bucks County and Montgomery County, Pennsylvania. As Al was saying, the rest of Pennsylvania is a wholly owned subsidiary of the gas industry, except for Bucks County and Montgomery County. And even the governor, who has been willing to give the state to the industry, even the governor is backing a study, which has just started, a 2-year study, about whether gas fracking should come to Montgomery and Bucks County in the Newark Shale. So the principal areas that we're going to talk about here are Marcellus, the Barnett, the Bakken, the Eagle Ford, and perhaps the Haynesville and Fayetteville are important assets for us. Now, radon and natural gas. The thing that's most alarming to me about this whole thing is when they drill these wells that they're going to frack, they figure out that they're in the shale based on the radioactivity level that comes back in the drill cores. But they say there's no problem with radiation. What we've got here now in the New York City area, and New England as well, is the gas that we've been burning for years has been coming from the Gulf Coast. And it has an average level of 5 picocuries per liter of radon in the gas. This was a study done by EPA back in 1970. It looked at all of these deposits that I was identifying before and looked at radon levels, and they ranged from single-digit numbers like 1.2, 1.4, up to 1,450 picocuries per liter. By the way, just to give you a context for this, the action level that EPA recommends, active mitigation, is once your level of radon gets to 4 picocuries. But there is no safe level, and you can get cancer from exposure to a lot less than 4 picocuries. We'll get back to that later. So back then in 1970, the average of all of the measurements across the nation that the EPA had access to was 37 picocuries per liter. Now, the source here of 5 picocuries per liter in the Gulf Coast will be important later on when we talk about the risks in the New York City, New Jersey area. In 1980, a researcher at the Department of Energy looked for the first time at the Devonian shales, which are dark black shales in northeastern Pennsylvania. One of the things we find is the darker the color of the shale, the greater the concentration of radioactivity in the shale. And he found that an average in the Devonian shales of the northeastern Pennsylvania area and eastern Ohio and northern Kentucky, of 151 picocuries per liter. Okay, here are some average levels he also found for certain big cities, Chicago, Houston, Denver, New York. Of all of the cities that he looked at, I think it was about 8 or 10, New York City was the lowest at 1.5 picocuries. And that is the number of, you start at 5 in the Gulf Coast, and you get to no more than 1.5 when you get to New York City. That number is actually probably a little bit higher, this is a little bit low, because it takes a while to get that gas. One of the questions I had when I started looking at this was, how fast does natural gas move in a pipeline? And the average speed is somewhere between 10 and 20 miles an hour, which seems pretty slow. But that's what it is. So when that gas leaves the coast to go the 2,000 or 1,800 miles to get to New York City, it's going to take 6 or 7 days. With a half-life of 3.8 days, the radon that starts out at 5 picocuries at the wellhead in Louisiana is going to have decayed twice. So it'll be probably down to something between 1 and 1.5 picocuries per liter by the time it gets here. Good news is that means that not a lot of lung cancer being caused by radon in New York City compared to other major cities. Bad news is there's still radon in the gas. More recently, researchers at the U.S. Geologic Survey, led by Liz Rowan, measured wellheads in 3 Marcellus shale wells that were selected by the industry, by the way, for the test, and came up with a range from 1 to 79 picocuries per liter, or an average of about 36, which compares very favorably with the old number from EPA. This is how it gets here. Isn't that easy? You just go to Arkansas and turn right. This is the network of pipelines. This little place down here near the coast of Louisiana is what's called Henry's Hub. Everything in the world goes through Henry's Hub. Until now. Now everything in the world goes through Ramapo, New York. Let's break this down a little bit. From our Energy Department, the Energy Information Agency, they've drawn these corridors. There's a regulatory background for that, but it's not relevant at the moment. But you'll see here the widest road, in other words, the greatest movement of gas, is from Louisiana up to New York City and New England, and Pittsburgh and a few other places along the way. Notice the other big ones. This one cuts right through the Bakken. This one cuts through the Eagle Ford. This is the Barnett coming in here. So let's break it down even further. There are 3 or 4 pipelines that are important here, and the fight that may be coming here with compressor stations on the Algonquin line in New England is important as well. This is the Texas Eastern line. Texas Eastern is one of the 2 companies in Spectra Energy that are bringing gas to Manhattan starting in early November, finishing the pipeline construction now. Well, most of the gas makes its way up here. And notice here, it's through southern Pennsylvania across north of Philadelphia, and actually, at the end of this is in Linden, New Jersey. You'll see the blow up of that in a second. But is there radon-laden natural gas coming to New York City now? The answer is yes. Gas companies won't tell you how much. But this is an active production area in southwestern Pennsylvania, and the pipeline cuts right through it. That's part of the Marcellus. That's one of the big areas of Marcellus. The other big area of Marcellus is up here on the New York State line in Bradford and Susquehanna counties, Pennsylvania. Texas Eastern doesn't reach it. What are these little things going off here? Well, these little things are lines that go to storage facilities, which are underground areas that used to produce oil or gas and now are salt and are now vacant. And you can pump gas in there and keep it there. Why would you want to do that? Why do you need to do that? You need to do that because of the market timing and the movement of gas. We burn most of the gas in the winter. We don't need as much in the summer. So the wells produce continuous rate. So what they do is they put it in storage in the summer and then take it out when they need it in the winter. Here's your favorite pipeline, the Duncan transmission line. By the way, it goes up past this, goes into Canada, all of Nova Scotia. And this is the key piece right here from Marsalis. Notice Ramapo right here. The Texas East, the Tennessee gas, the Millennium gas pipeline, the Iroquois line from upstate New York and Canada, they all come into Ramapo. And what the Spectra project that is now being completed, not only is a line from Linden, New Jersey to Manhattan into the Hudson River, but they did one other thing. The Algonquin line runs this way. All the gas moves this way. Not anymore. This little red piece here from Mawa to Hanover flows this way. And what does that do? That lets gas that comes to Ramapo and then down to Mawa go down here to connect to the Texas Eastern line, to go to Linden, and then into New York City. So this is the link that is going to bring Marsalis, more Marsalis gas to your apartment in the city. Here's the other one that's relevant here, that's the Tennessee line. Again, it starts down here in Henry's Hub and Louisiana and Texas. And this time it goes through northern Pennsylvania. And Bradford and Susquehanna counties are up in that area, and that existing line goes right through and comes into, going this way and down here, Ramapo, New York. Took forever to figure these damn maps out and find access to it. And we kept hearing Homeland Security was going to keep you from getting at this. Well, we discovered the Information Agency site, and they said, oh, it's okay. But you don't get anything much more than cartoons like this. This is the Millennium Line. This is going to pick up from all of the southern tier of New York. And by the way, they're developing gathering lines that go from northeastern Pennsylvania up to the Millennium. The Millennium goes to Ramapo, New York. This is the detail on the Spectra pipeline. Here's the piece I was talking about that's going to carry Marsalis gas from anywhere up in this area where Ramapo is down into Linden and then into Manhattan at the Gansevoort Peninsula. Okay, let's just do a little, this is the calculation. This is math class. Math class was usually the first period. Couldn't start. It's been a long time. I think I finished high school the same year they invented dirt. But just doing the math, at 10 to 20 miles an hour, 10 to 12, I guess I used here, to get from western Marsalis, the western area of Marsalis and southwestern Pennsylvania, and the Morgantown, West Virginia area, here's what we got. It takes 40 hours, so if you start with 79 picocuries, which was the average, which was the high figure from the more recent USGS studies of the 3 wells, then it declines from 79 to 45 or 50 by the time it gets to Manhattan. Remember how much there was? 1.5? How would you like to go from 1.5 to 45 to 50? What do you think the risk threshold is on that? We'll get to it. From the eastern and northeastern, from the Hancock, New York, that's where the Millennium Line crosses, as I was mentioning before, and Bradford and Susquehanna County. Now we're talking about 12 to 15 hours. If you start with 79, here's the numbers you're going to end up with when you distribute the gas to consumers. You hear about norm, and the industry says, well, norm is just natural. We can't do anything about it. And that's true, but T-norm means anything that man has touched and augmented in some fashion and changed the sort of the equation. And so now regulation relates more to what's referred to as T-norm. There's another principle here that should be driving any regulatory action in this area, and that's what's called the alarm principle. It's kind of like the precautionary principle that you should keep exposures as low as reasonably achievable. That's what it stands for. And this has been the operative sort of mainstay of all the regulatory activity involved in nuclear power and anything with nuclear materials. But it has not yet been applied in this context. There are various studies going on about these risk levels, but they all seem to come out the same ultimate response at low levels. They all accept using the linear non-threshold dose-response model. That's what's called the one-hit model of carcinogenesis. This is an ongoing study about, unlike radiation is controllable, it was placed there by man, and should be controllable, unlike radioactive materials not generated by man. Finally, let me give you sort of just a snapshot of what the current status is. At the moment, there is essentially no EPA regulatory control over radon or any other radioactive materials in natural gas. There is, historically, there are drinking water standards, 15 picocuries per liter of all alpha emitters, 5 picocuries per liter of radium and radon. The Clean Air Act has national emission standards for hazardous air pollutants for certain source categories of emissions, but the only areas that they have adopted regulations related to radiation are uranium mills and uranium mines and elemental phosphorus plants and phosphogypsum stacks. We don't have any of those up here. And finally, the Comprehensive Environmental Response Compensation and Liability Act, which is known as CERCLA or Superfund, does have guidelines that are not numerically specific, but generally narrative for soil remediation and groundwater remediation. And generally what you'll find is that the MCLs, the maximum contaminant levels, are applied to groundwater remediation projects that are superfund. So what we have is at the moment very, very little, if any, regulation directly of the radon levels or other radioactivity either in the wastewaters or, more importantly, from my perspective, in the gas, which is the product of all of this effort and is coming to our homes. So we're exposing millions and millions of people to increased levels of radon. Now, the industry likes to say, well, these numbers don't mean very much, they're negligible, 17 picocuries at this spot or that spot, by the time it gets to the city, doesn't mean, maybe at 15, that's negligible. But guess what? 15 is 10 times more than people in New York City have been exposed to from natural gas in the past. 21,000 deaths per year are attributed to radon by EPA and the Centers for Disease Control. And that's at a radiation exposure level of 4. New York City has been in a better position than that historically. So what do you think is going to happen with the incidence of lung cancer, even if we just multiply the exposure level by 10? And frankly, as you saw from some of those numbers, we're going to be increasing the exposure level by 50 to 100 times what it has been in this area. And that's why one of the things we're trying to do now is get a handle on this, both with the Federal Energy Regulatory Commission, who pretends that radon doesn't exist as an issue, and with the local distribution companies that are outside FERC's jurisdiction. All of the distribution of gas in Albany, for example, or in Manhattan, or any of the boroughs in New York, or northern New Jersey, is all done by a local distribution company like Con Ed, or I forgot the New Jersey company.
PSE&G.
PSE&G, right. Yeah. Those are not subject to FERC jurisdiction. That's why we're working with Assemblywoman Rosenthal on the legislation to try to apply some requirements to reduce the levels where the gas is coming to New York. Can it be done? Yes, it can be done. How can it be done? Well, remember, there's only one way to create radon. There's only one way to get rid of it. Radioactive decay. With a four-day half-life, roughly, if you hold on to that gas for 30 days, you're going to reduce the radon level by 2 or 3 orders of magnitude. So storage is a way to deal with this. Another way to deal with this is processing. If you refrigerate the gas, at some point the radon liquefies and comes out of the gas. That point is at minus 61 degrees centigrade. When you're processing gas, you're trying to get the gas liquids, the petroleum liquids, out of the gas. The most valuable of those is ethane, which is used as a feedstock in almost all chemical processes. That, when liquefies at minus 160, roughly, degrees centigrade. So enough refrigeration, you can remove most, if not all, of the radon. But it takes time and it takes money. And there's no commitment that's been made to the Federal Energy Regulatory Commission on any of these pipelines so far that there would be storage or processing sufficient, focused on reducing radon levels in the gas to the point of where they would be comparable to the exposure levels people have had in the past. So that's where we are at this point, working on these issues. We'll get to questions later on. Let me hand it over to Sheila.